Thank you, Steve, for a very kind introduction. I think he's said most of what I'm going to say today, in fact. So well, here we go. So yes, I'm going to tell you about the past 20 years of VERITAS, and a bit about what gamma ray astronomy is, some of our accomplishments. But one of the key accomplishments is quite literally the fact that we've operated for 20 years. VERITAS was built to go for 10 years, and that we're still going 20 years later is an accomplishment in and of itself, and a testament to the quality of the equipment and the efficiency with which we run it. There we go. So let's start out with what is gamma ray astronomy. Well, when I was a boy, the first time I had ever heard of gamma rays was from the Incredible Hulk, and that it had turned Lou Ferrigno into this monstrous green thing. And it was actually quite terrifying, and I never realized that I'd spend much of my life chasing gamma rays after that. But what we need to realize is that gamma rays are just light. They're the most energetic form of light. And VERITAS studies what we call TeV gamma rays. These are photons of light that have what we call an energy of 1 trillion electron volts. Now, I'm going to shorten that to volts just to keep it easy. And we've heard trillions when we talk about the federal budget, and it starts to become a number that rolls off a tongue. But what is a trillion? Well, that is a 1 followed by 12 zeros. So that is a million million. That is really a lot of zeros. And in terms of energy, an optical light, which we're familiar with, and you can break it up into a spectrum where you have red light, blue light, purple light. Optical light has an energy of 1 volt. So when we're talking the gamma rays we're talking 1 trillion times more energetic than optical light. Okay. So what do I mean by things, have energy? How do these, photons get this energy? Well, we're used to thermal radiation. You stick a piece of metal into a forge and it gets hot and it starts to glow. Okay, this is called thermal radiation. And as it gets hotter and hotter and hotter, it tends to get bluer. Okay. All right, well, but that's not where gamma rays come from. The hottest objects in the universe are about 10 billion degrees Celsius, but this is only 1,000 volts. Okay. So we're talking 1 trillion, which is really a lot more than 1,000. Most of us probably can find $1,000 somewhere. None of us are going to find $1 trillion anywhere, right? So what is going on? And the trick is that 1 trillion electron volt radiation is non-thermal. It's not just from heating something up to be super hot. Okay, this is something that's produced by particle accelerators. And so I show you a picture over here of mankind's best particle accelerator. It's called the Large Hadron Collider. It's in Geneva at a place called CERN. And this can produce particles that are 10 trillion electron volts. Okay, this is the best thing mankind has ever built. But to produce 1 trillion electron volt light, we need 100 TeV particles. So mankind can't even produce the light that VERITAS is studying, or the particles that make this. And so we study the biggest, fattest particle accelerators in the universe, and obviously these things are in outer space. And here's a picture of one of these things. It's called an active galactic nucleus. And this is my specialty when I do astrophysics. So we're not looking at thermal radiation, things that glow hot, glow bluer when they're hotter. We're looking at particle accelerators. And if you want to take anything away from all the objects you look at, this is a diagram of power versus energy. And everything we look at, in these up in the sky has 2 bumps. Okay, there's a bump here where it peaks somewhere in the optical, so this is radio, and it gets brighter towards the optical, then it falls off at X-ray. Then it starts coming up, getting brighter at gamma rays, and then it falls off again. Everything looks like this in the sky when we talk about these non-thermal particle accelerators. Whether they be supernova remnants, whether it be binary stars, pulsars, active galaxies, you name it, they all have a double bump sort of structure in the emission. And these things slide around. They may be a little bit brighter, they may be dimmer, they may be brighter in X-ray, less bright in optical, but they all kind of behave like this. All right, so Cherenkov astronomy. This is what we do. How do you detect gamma rays? Well, it's called Cherenkov astronomy, and it starts with a guy named Pavel Cherenkov. He discovered Cherenkov radiation in 1934. Okay, he's a Russian guy, and he ended up winning the Nobel Prize for it in 1958. It takes a little while to issue these prizes for doing these type of things. And what is Cherenkov radiation? Well, when a particle is moving at the speed of light in a vacuum, nothing funny happens. But when it's moving at the speed of light in a medium, say, air or through glass or something, you can actually move faster than the speed of light in that medium. So it's like you can't move faster than the speed of light in a vacuum, but you can move faster than the speed of light in glass. And when you do so, light gives off something, light's version of a sonic boom. It's this ultraviolet blue radiation called Cherenkov radiation. So he got the Nobel Prize for discovering this. And in 1953, the origins of our field, a guy named John Jelly decided to try to detect Cherenkov radiation from particles moving through the atmosphere. And he instrumented a trash can, because this is low budget stuff here, with a photo sensor. And this became the origin of gamma ray astronomy, with our nice little trash can right outside a lab in Dublin. And sure enough, it worked. Okay. All right, so how does gamma ray astronomy actually work? Well, what you do is you have a cosmic source of gamma rays. This is the Crab Nebula. It emits a gamma ray, it starts coming down to us, and we can't actually detect gamma rays on the ground. The gamma ray hits the upper atmosphere, and it creates an explosion, a particle cascade, which grows and grows and grows. And as it's moving down towards the Earth, these particles are traveling faster than the speed of light in air, and they give off Cherenkov radiation, this ultraviolet blue light. Okay, and this pool of light grows and grows and grows till it's about 300 meters across, about 1,000 feet across. And all you have to do is stick a telescope in that pool of light on the ground, and you've detected a Cherenkov radiation, and hence the gamma ray. And you can, so it's quite a nice thing to do. You can put a relatively small telescope in there to detect this gamma ray. And if you put more telescopes in there, it turns out to be a bit better. And why do you want to do this? Why wouldn't you fly a satellite? Well, you can fly a satellite to detect very low energy gamma rays. There's something called the Fermi satellite, which you see here. But to detect very high energy gamma rays, you need to fly a satellite that's bigger than a football field. And there's nobody that can fly a bird that big. So we have to do it this way on the ground. Turns out it's not that easy. Uh-oh. Okay. So the early work, everybody was like 1960s, everybody's optimistic, the space race. We start trying to do this. Okay, and a bunch of people, some people in the Ukraine, some people in Ireland, some people in the United Kingdom decide we're going to try to do Cherenkov astronomy, TV gamma ray astronomy. What they did was they instrumented some World War II searchlights, and rather than like taking light, broadcasting it upwards, they were going to take the light that's coming down, reflect it back onto a photo sensor. And so they tried to do this, and it didn't work so well. Okay. Shot one, not so great, but you have to start somewhere, right? Oh, there we go. So in 1967, they decided to try to do something a little bit better. My predecessor at the Smithsonian, Trevor Weeks, and a graduate student who's still based here in Tucson, Arizona, George Ricci, they brought out one of these searchlights to do some work here in the desert down by Amado, okay? And they were trying to search for this Cherenkov radiation, but really, what they were doing was going to build a bigger telescope. But what you can see here is they pulled off, out in the Coronado National Forest, set up these searchlights to do the search. But when you look at this picture, if you look in the background, you can actually see that it matches. This is the home of the Whipple Observatory in VERITAS today. So, 60 years ago, give or take, they had, had designs on things to do this type of study. But really what they came out here to do was to build the first real gamma ray telescope. It was dedicated in 1968, and it's a 10-meter telescope, so that's about 35 feet across. Okay, and the idea was the light came in, the Cherenkov light came in, it focused here, and it bounced it up onto a camera. But the camera had 1 pixel. Everybody's iPhone's a lot better than that. It was a simple pixel. The pixel had a 1-degree field of view. To give you an idea of what a degree is, the moon is a ½ a degree across, so it was viewing twice the moon diameter in size, so pretty rough. And it used something called scalars, where anytime a piece of light hit that pixel, it would trigger, and then it would just kind of count. So photon, 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 and it just used a stopwatch. It had a second pixel off to the side that would count the background. Maybe this will work. Well, it turned out it didn't work so well. Tried for 20 years, and it's really radical technology for this time. My grandfather was a physicist. He was developing these type of machines that were using it. Just to build these machines was, a monumental achievement. So they tried and tried for 20 years. It actually got shut down in 76, restarted in the early 80s, but basically there was no credibility in this field. But finally, in 1983, we got some money from the Department of Energy. And the problem is that the background, if a gamma ray source is out there, the brightest source out there, the background outnumbers the gamma rays 10,000 to 1. So if you're just trying to count things, you're never going to see gamma rays. Just never, ever, ever. So what they realized, they started doing some simulations on some computers. And mind you, this is the era of the Apple IIe, not some really powerful hardware there, right? Did some simulations, and they realized that if you looked at a gamma ray coming in with a little bit of resolution, you could actually see a difference in shape. It looks like an oval, whereas the background looks really clumpy and kind of weird. And so if you had a little bit of imaging, you might be able to discriminate things. And so they built a 37 pixel camera. Okay, still not too many pixels. But after 100 hours of data in the mid-80s, they managed to detect the Crab Nebula, and the plot of that detection looks something like that. By 1988, they managed to get to 109 pixels, and it went from 100 hours down to 25 hours. And then by 2000, 300 pixel camera got it down to 1 hour. So we went from not being able to see anything to 100 hours to 1 hour in about 15 years. And then by about 2000, when I got my PhD, there were 6 credible sources of gamma rays. Still very much in its infancy, still a lot of debate. And during this time, there was an evolution of things going on. My friends in Germany, they decided, they're not going to build a 10-meter telescope. They're going to do 4-meter telescopes, much smaller telescopes, but there are going to be 5 of them. They're going to be on a square of about a football field aside, and one in the middle. And what you notice if you do this type of thing is that the background is 10,000 to 1. 2/3 of it is just from a particle radiating light just above the telescope. And so if you have 2 telescopes that are separated, it won't see that other particle. And so you can just say, did you see it? Did you not? And you reject it right away. And so that helps quite a bit. The other thing is you can average out the shape. Is it oval here or is it round over here? Things like that. And so that worked even though the telescopes were quite small. As I mentioned before, getting more pixels made things a bit better. And our friends in France, they built a 548 pixel camera with some really fancy electronics. Okay, as you see here from Cat, they built it in the Pyrenees. And the biggest problem with this telescope, which was probably the best, was that it always was cloudy. Of course, the Pyrenees is up in the Alps, and there's some really great skiing up there. And so I think my French colleagues knew what they were doing because, we're clouded out, let's go skiing, But in any case, by 2000, all these ideas had the similar sensitivity. Once again, seeing the Crab, the brightest source, in about 1 hour compared to about, 100 hours 10 years before. But it gave us the idea that an array of 12-meter telescopes with high resolutions was the clear path forward. And that's where VERITAS comes in. So 2004, here's the VERITAS prototype. Okay, we're going to have 4 12-meter telescopes. And you can see the prototype. It only has, about 1/3 of the mirrors, okay? It only had half of the camera instrumented, this side over here, but it detected the Crab Nebula in 1 hour. So it's already good enough. It also detected an active galaxy at 20 sigma. You can see a nice, clear, strong signal there. That's the signal, that's the background. Looking pretty good. And then by 2007, she's up and running. We have 4 12-meter telescopes on a square of about 85 meters side. So again, about a football field's distance there. There's only 500 pixels in those cameras. And that doesn't sound terribly impressive, right? Everybody's got 10 million pixels or so in their pocket. But we take 1 billion pictures a second. Okay, so there's a lot of fast electronics in there to read this out. We got supercomputers crunching the data. You name it. You have to write a lot of software to do this and train people how to handle it. Okay. So we began full-scale operations in September of 2007, and as you heard before, we're just down the road, about 20 minutes away at the Whipple Observatory in the Santa Rita Mountains. This is what she looks like today. We have 4 VERITAS telescopes, and in the background, we have a prototype telescope from a next-generation observatory. The thing you'll note there is that it actually has 2 mirrors instead of 1 mirror surface. And I'll come back to that. So looking at a little bit of the hardware, the first thing you notice on VERITAS is that it's a 12-meter dish, but it's segmented. It's got 60-centimeter mirror facets. You don't need to have very expensive optics. This makes it lightweight and affordable to produce. So there's 345 mirrors. They're about $1,000 each, so $300,000 mirror surface. If you were trying to build a 12-meter mirror, it would cost several $1 million and weigh a ton. You also couldn't put it outside in the elements. You couldn't take the mirrors off and recoat them when they get weathered, things like this. You can see the camera right here. It's open. It's about 2 meters across, about the size of a small car. But then once again, you have all the fancy electronics in there that allows you to take 1 billion pictures a second. So where does VERITAS stand in the world? Well, we're here in Arizona, okay? There are 5 major projects in the field. There's something called HESS. I worked for HESS for about 5 years back in the early 2000s. There's a project called MAGIC. HESS has 4 12-meter telescopes and a big 30-meter monster. MAGIC are 2 17-meter telescopes. And there are 2, quote, all-sky monitors, which are basically water tanks that do things a little bit different. They detect the particles rather than Cherenkov light. But we're the most sensitive observatory in the world, and we see the crab in under 30 seconds. All right. Think about 100 hours in the mid-80s down to 30 seconds now. Lots of progress. And it's going to get even better. We're going to talk crab in a second, soon.
Here to ask, are y'all connected?
We talk to each other. We're all good friends.
Oh.
Put it that way. So we've had an explosive growth in the field. Like I said, in about 2000, there were about 5 gamma ray sources. You can see the map of all the sources on the sky right now. This is in what's called galactic coordinates, where this is the plane of a galaxy. And these are all the sources that are outside the galaxy, okay? And you can see there's a really explosive growth. The X-ray astronomy debuted in the 60s, and it's been growing, and now you have millions of sources. There's a lower energy gamma ray astronomy, which started in the 70s with satellites. It's basically satellite gamma ray astronomy. And, there's 5,000 sources now. And now we're up to about 300 sources. There's 10 or so different flavors of these objects. It's just growing, order of magnitude, factor 10 per decade, give or take. And so we're really growing, really kind of becoming mainstream. All right, well, I mentioned this thing called the galactic plane. Oh, sorry. And so we are out here. This is kind of a view of the Milky Way. We are out here right on the edge of one of these spiral arms. And if you look towards the center of a galaxy, you can get a sweeping view of a galactic plane. What do you see if you were looking with VERITAS or with my friend's instruments called HESS? And when you look across it, just going from left to right, it's going across, you hit the center, going across. You can look at it with this, or you can look at it with higher energies. You notice a few things. You see a bunch of different dots. Okay, they're point sources, they're bigger sources. There's diffuse emission, kind of this just blob of just very nebulous stuff. This is from cosmic rays interacting with matter, things like that. So there's a wide variety of things that you can see, and I'll explain a few of those things as we go here. One of those things are supernova remnants. Okay, they happen in our galaxy a supernova happens in our galaxy once every 50 years. It's the death of a star, and basically what happens is when a star runs out of gas, okay, is basically this nuclear reaction going on inside the star, and as nuclear burning's happening, it's exerting pressure outwards. But when it runs out of gas, there's no more nuclear pressure, and all the material from the star starts to fall in under gravity, and it gets going faster, 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 and then it bounces, and boom, you have this massive explosion. Another thing that can happen is if a white dwarf gets too fat, gets too much matter on it, it can also create a runaway explosion. There's different types of supernova remnants, and it can be briefly brighter than the rest of the galaxy. And so you can actually see these things during daylight when they go off, and there's like records, there's cave paintings, ancient Chinese drawings of these things going off. And so it's pretty cool. But what happens is they expand outwards, you get a shell-type structure that looks something like this. And there can be a central object. This is the crab pulsar left behind for some. And many of these objects are detected in the gamma ray band, at TeV energies. Okay, other things that we see are called pulsar wind nebula. Okay, and what happens is as this remnant goes out, you can imagine it's expanding into a uniform medium. So this, explosion's going outwards, pushing on the matter, and it's pushing things out. But what happens if there's more matter on one side than another? Well, it's a lot harder to push into the part where there's more matter, right? So it's going to push a little slower, right? And on the side where there's less matter, it's going to push more quickly. So you can get odd shapes. And of course, nothing's like, oh, it's half this side or half this side. So you get really irregular shapes. But you get a cavity inside that looks a little different. And what can happen is there's a pulsar left behind, which is a neutron star and has magnetic fields. And this thing is spinning. And if you have a spinning thing with a magnetic field, it accelerates particles. I'll leave the physics lesson behind. But you can imagine that it accelerates particles. And these particles then give off gamma rays in this medium. And so you get all kinds of weird shaped objects. Sometimes you get the shell. Sometimes you get the medium that's filled up. Okay, and you can see that a lot of the things we see have this weird blob. And if you see these contours here, that's the actual shell as seen in a different energy. So sometimes we'll see the shell, sometimes we'll see the blob in the middle. And this is a lot of what you see within our galaxy. So here, this is I chose a Hess image because I think it's one of the prettiest. This is a shell-type supernova remnant where you see the matter hitting the clouds on the edge. That's the moon, just for scale. So these things are huge. Okay, this is what's called a pulsar wind nebula, where it's filling the void. And what you can see here is it has a different shape depending on what energy of gamma rays you're looking at. Very bright at low energies. Okay, a little bit, about the same brightness at moderate energies. Oh, wow. Now you're getting higher energies. It's very compact and small. And then you suddenly don't see it. And it's because the different energy particles cool on different time scales. So it'll change its shape and structure. And as you make these measurements, it gives you a feel for what's going on in the object. And our modelers love these types of pictures. But one of the things you'll note on the galactic plane is that when you find these objects, and they have all kinds of different shapes and sizes, and here's just a selection from my friends from Hess, is that astronomers don't know what half the objects we see are. They're not seen in any other band. And then we used to call them dark sources, and that got people all excited. Oh, you see dark matter. And like, no. If we saw dark matter, I'd be giving speeches in Stockholm and stuff like that. That's just not the case. But what really it is that these things can just quite literally, remember that double hump structure that I showed you? They can quite literally just be very, very bright in gamma rays and not bright at optical or X-rays. And so you just might not see them. And so we have to mobilize the community to explore all of these different things. And these things are just coming in so fast now that it takes too much time to identify them all. And so we have to set up these projects and these campaigns. And it's just going to take years and years and years to understand all the things we're seeing. So again, my specialty are active galaxies. Okay, what are these things? Well, we all know galaxies. There's billions of them. At the center of every galaxy is a supermassive black hole. Everybody likes black holes, mysterious objects. Okay, most of them have a black hole that's millions or even billions of solar mass at the center. Okay, and about 5% of these things have an active galaxy. Okay, these are very young galaxies. And what an active galaxy is a galaxy that has a whole lot of matter right around that black hole that's spiraling in onto it. Okay, you have a disk and maybe something called a torus. Just think a tire around it, or a donut, if you will. And that matter is spinning in. And in about 5% of these things, that spinning in creates a jet, a structure. This is like a collimated beam, if you will, a death ray. Kind of fun to think about that. And this is, it doesn't quite look like this model. It's a little bit more, convoluted, as you see over here in the artist's image. But these jets create gamma rays. And then what you see depends on whether this jet is pointed right at you or if it's a little bit off axis to you. It could also be if it's, way off axis and you're obscured by the donut there. All of these active galaxies, there's like 100 different flavors of them. Depends, like jet, no jet, donut, all these different things. Okay, but the ones that we most love are where the jet's pointed right at us. Okay, it causes, when the jet's pointed right at us, to make these things to be extremely variable. And so this is a picture I made, well, it hurts to say, 22 years ago. And this is a plot of the light coming from a galaxy. Okay, this is the brightest gamma ray source in the sky, this dashed line. Normally, this object is about 8 times less bright than that. Okay, and then one morning, I asked the Hess Observatory to take a look at this thing because I knew something was going on, and so they did. And what you can see here, these are 90-minute observations. Every point is 1 minute. But you can see this entire galaxy is varying by almost a factor of 100 in brightness. Now, it's not the whole galaxy itself. It's just the center region of it. But you can imagine it's just going up and down, up and down, up and down. This is the most extreme thing that anybody has ever seen from a galaxy. And it led my predecessor, Trevor Weeks, to describe it as photons from a hotter hell, because it is just, absolutely crazy. That's what they call it in the nature description of this thing. But the main thing I want you to take away is that these things can really move a lot. If you imagine a galaxy changing its brightness by a factor of 100, not a star, a galaxy, billions and billions of stars. So what do we see with VERITAS? Well, we don't look at the moon. We don't look at planets. You see Jupiter and Saturn up there. This is what we see with VERITAS. Galactic objects, we have 70 different things from 8 source classes, mostly extragalactic things like AGN. It's about 70% of our catalog. We do a little bit of galactic stuff. This is galactic coordinates. The reason we do less galactic stuff is the galactic center is here, and it's very, very low to horizon. It's really a southern hemisphere thing. So we're only limited to seeing this part of the galactic plane. Okay, but 70 sources, if you think about when I started where there was 3, just the idea of having 70 is truly amazing. So TeV, AGN are my specialty. Okay, here are 3 that we discovered this year. This is my baby. You know, I kind of devoted my career to try to get as many of these as possible. Okay, and what you can see, and there's a lot of information on this plot, is the main thing I want you to take away is it takes you about 50 or 60 hours of observations to discover these things. And you see, we started in 07. And what ended up happening was we got a little bit of hint of something, but then we realized, oh, it's going to take us a real long time to finish it. So we wanted to kind of prioritize, you know, some other, let's say, lower hanging fruit before coming back to it. So this is kind of what we're doing now, is coming back to all these things. Oh my gosh, that's going to be real hard. Let's do that in our later days and try to get some other nature paper stuff. But it turns out that these objects are very, very interesting. This is a nasty plot. I don't want to explain to it, but we're trying to find things up in this corner. And what does things up in this corner mean? Well, if you're up in this corner, it means you're likely to give off particles called neutrinos. There's neutrino detectors down. There's one in Antarctica, and they're building another one in the Mediterranean Sea. And if you're up here and we see you, if you give off neutrinos, you give off gamma rays. And so, and vice versa, if you give off gamma rays, you may give off neutrinos. And so we're trying to find objects from neutrino detectors, and those are, you know, what's called billion-dollar class observatories. And so we're trying to make it a little easier for them. And so this is what I've been out there hunting, and that's what these objects are for. So we're trying to make it a little bit easier for our friends. Other things. When we first started in this business, there were all the AGN that we were finding were called high frequency peak BLX, that are these things. And this is TeV gamma rays. You see that, okay, you can probably see those, but there are other types. And what you see from this plot is that, oh, they get less bright when you get to the TeV band. So I've been trying to find other types. Okay, and we found 7 of these guys. We found 4 spectrum radio quasars, and we found 4 radio galaxies. Radio galaxies are not when you're looking down the beam, but off axis. Okay, so we're trying to find different flavors of things. But of course, we're not just stamp collecting, and this model is crazy. It's going to be hard for anyone to decipher. It would probably take me a half hour to explain it to somebody. But what I wanted you to see is that you start throwing a model. This model over here is what everybody used 20 years ago to explain all of the active galaxies. And with these new types of AGN, you see the line, looks okay, looks okay, looks okay. Uh-oh, it's starting to miss the points over here, right? What you see here is that we make the model a little bit more complicated for these new types of AGN. You see, oh, it runs through. And this is a project that's being done with my student, is that now we're seeing new classes of AGN. This is a new type of satellite. It was just launched a few years ago. So we have better data, and we're actually starting to able to take this model, which everybody called the spherical cow, if you will, and we're trying to make more complicated things to understand what's going on. So we're finding different types of AGN, and we're actually understanding how to do it beyond the most simplest assumptions. And obviously I can come back and explain things more, you know, to the side, but I need to keep moving. So obviously we look at things with the Milky Way in VERITAS. You can see the Milky Way right there. We can see things in the galaxy. What are some of the things we see? Well, we look at binary systems. And so here we have a compact object. It's a neutron star in orbit around a massive star. And this massive star is a really big star with a disk around it. And as this thing goes around, it goes through the disk, and all kinds of crazy things happen. And we get all of our friends together and we look at it. We looked at it for 220 hours. It's about 450 hours of data here. We get about 1,000 hours of data a year. So to give you an idea of the scale of this project. And what you do is you see as you go around this circle, so this is one phase is this whole loop around. You see that it goes up, you hit the disk, something crazy happens, you exit the disk, something crazy happens again, and you just loop around. And you can see that you can make a period for it, okay? And you can see our friends in X-ray do the same thing. And this is the first time in TeV gamma rays that you can now start classifying objects as, oh, this is a binary system. This is like a really radical thing to do. Optical people have been doing it for centuries, right? But like for gamma ray people to be able to do it, you know. And you can't actually see this stuff in optical. So for us to be able to identify binary systems in gamma rays is major progress. Okay, everybody loves supernova remnants. They're really pretty. So this is the Tycho supernova remnant. It went off at about 1600. Okay, this is what it looks like in gamma rays. Not quite so pretty. In fact, you can see this image right here overlaid. And that's because our point spread function isn't quite as refined. You know, we're still early generations. The next generation will have 3 times smaller circuit here. Okay, but what can we do with this thing that's really cool? Well, we see it, that's great. But what you can do is you can start making measurements and combining with other things. You have a radio telescope, you have an X-ray telescope, you have a Fermi satellite and a VERITAS satellite. And you can start to model this. And what you want to try to ask with these gamma ray sources is, you know, what is creating the gamma rays? Are you accelerating electrons to make these gamma rays? Or are you accelerating protons? You know, I think we can all remember a little bit of our basic physics from way back in the day, okay? And, you know, a big question throughout time has been, if you accelerate protons to make from supernova remnants, you might find the origin of cosmic rays. And I'm going to come back to this. And so when VERITAS detected this, you said, okay, well, what type of thing is it? And when you make the model, if it has a bump going upwards, it's proton. If it turns over like this, it means it's electrons. And so we found the first signature for proton acceleration in a supernova remnant, which was a really big deal. If we move forward, we looked at another supernova remnant called, well, IC 443, or the jellyfish nebula, which is way more fun. And you can see this bump once again, another hadronic bump. So you're clearly starting to see that supernova remnants accelerate protons to very, very high energies. Okay, and you can also see that this thing's shape, like I said, changes with energy. Here's high energy, here's low energy. You know, it's very, very bright on the spot here, but off to the side at the highest energies, it is brighter over there. But the main thing to remember is that we're accelerating protons. And why? Because we've been searching for this pot of gold, you know, with VERITAS for a long time. I took this photo and I actually walked over right there to where the rainbow ends, and there is no pot of gold. I'm sorry to inform you. And the reason is these things called cosmic rays. In 1912, Victor Hess went up in a balloon with some, you know, very early detectors, and he thought that this ionizing radiation would decrease as he went up in sky in this balloon, and he actually found that it increased. Okay, and he won the Nobel Prize for this thing. And these things called cosmic rays, which were the origin, you know, these things, the origin is still a mystery. Many people have thought that they've, you know, come from these supernova or supernova. But in order to do this, you have to detect 100 TeV gamma rays from supernova. Well, we saw that we've done that. We have to show that they come from hadrons or protons, which I just showed you that bump, if you remember. But the last thing you have to do is, okay, well, that's great, but you have to show that many, many supernovas generate cosmic rays. You can't just have 1 or 2. You have to have a lot of these things, right? Because these cosmic rays are everywhere. Like you can't fly with a radiation badge in an airplane because there's so many cosmic rays, it'll contaminate it. So this is where we do this. We look at starburst galaxies. A starburst galaxies form when 2 galaxies interact. They come together, they collide, and they create a very strange looking thing like M82, which is called the cigar galaxy. And at its core, it creates a region called a star formation region, which has a lot of stars that are born, but corresponding a lot of stars that die. And if stars die or supernova, then you have a lot of cosmic rays, right? There's also a lot of gas there from when these things crash together. And so if you have a lot of supernova and those things make cosmic rays, and if you have a lot of cosmic rays and there's a lot of gas, you'll get a lot of gamma rays. Oh no. And so here we are. So when I first started running VERITAS, this was like the top priority. And so we looked at M82 for 175 hours in the first years of VERITAS, and it came out to be a Nature paper. We've actually looked at it now for almost 400 hours. We just published a paper this year. And lo and behold, we detected M82, the cigar galaxy I just showed you. You can see the most recent picture right here. It took us 135 gamma rays and 235 hours of good data. That's less than 1 gamma ray an hour. So this is a business of patience. And what we find if you start taking the models here, this is the gamma ray data. This is VERITAS, something called Fermi. This is some X-ray data, some radio data. Is that the cosmic ray density in M82 is 500 times that of a Milky Way. So really a lot of cosmic rays. And what we also find is that if you try to draw a line through this data, using various, models and supercomputers, is that only models for protons work. So it really has to be generated through, accelerating protons and those hitting the gas. And so if you start really working through all this, if supernovae are a primary source of cosmic rays in the Milky Way, the density that we measured in M82 requires a rate of about 10 to 30 times higher supernova in M82, and that's precisely what is observed by others. And so basically this means that we found a smoking gun for the supernova origin of cosmic rays. And so it's a 100-year-old mystery. Leslie Sage demanded that I try to say this in Nature and put out press releases. We tried to be a little bit more cautious because, 100-year-old mysteries deserve respect. But it was our pot of gold for VERITAS. And everything keeps pointing to this. But VERITAS is unusual. Last year, we all may have seen the aurora that came through. This is what it looked like at the Whipple Observatory. It was actually so bright we couldn't operate the telescopes. Our photosensors are so sensitive we couldn't turn on. It was saturating out our pictures. But we also look at unusual things. You may recall I mentioned that many of the sources in the TV sky are unknown. Okay, there was something called TVJ 2032. It was discovered in 2002. It was the first unidentified source. And everybody had a field day trying to explain what it was. Gamma ray burst remnants, dark matter, dark accelerator, you name it, lots of fun. Okay, well, we observed it for 50 hours, came up with the best ever detection. And you can see it here in the gamma ray band, and you can see it here in the infrared band and various other wavelengths. And what you can see here is a void. Remember how I talked about the supernovas sweeping out a region right here? And lo and behold, that's where the gamma ray emission is. And so you see this extended emission region. It doesn't have any energy-dependent shape, but the void we see matches that in the radio, and it turns out to be one of these pulsar wind nebula. And so we figured out what it was with this very in-depth study. And if I were a betting person, I never gamble, I will say that almost all of these dark accelerators or unidentified things are these pulsar wind nebula, but it takes you 50 hours to figure it out. So it's a lot of work. But what's really cool about this thing is that it is also a binary object. And so there's a pulsar in this system, and it turns out to be in a 50-year orbit around a massive star. And so in 2017, it was coming right in, and so we subtracted out the background level of gamma ray emission, and we ended up seeing that, kind of came in and the emission peaked, and then it went away again. And so we actually discovered that, okay, it's not just this pulsar wind nebula, but there's also a binary system in there giving off emission. The next time it'll roll through is 2067. I'm going to be in my, mid-90s. I don't know if I'll get to see that one, but, it's a once-in-a-lifetime event that we got to see. And so it's pretty cool. All right, here's the Crab Nebula. It's astronomy's most well-studied object. It's the brightest source in the TV sky, and we see it in 30 seconds. You'd think we'd know everything about it, right? Turns out we didn't. Okay. Turns out the Crab flux varies periodically. So you can see the VERITAS emission here. You fold it with the period of a pulsar, and you see a bump, and then a bump. And it's called a phasogram. So it's got a periodicity 33 milliseconds, so about 30 hertz. And so what you see here is the spectrum of this. And everybody and their brother told us that, the spectrum will fall off on this curve. Nobody would ever have considered anything else. This is power versus energy. Well, how on earth did VERITAS see it? They had to throw away all the pulsar models and start over again. Mind you, this is the most well-studied object. Everybody thought they had it down from the 60s, So turned out that we created some more mysteries for people. Okay, so we look into the mysterious. We're also pretty inspirational. An artist from a local community painted us this picture right here. It's pretty nice, and it inspires artists, but it also inspires us. So When I came out here, you remember in the early days, there were only 5 gamma ray sources. So we were pretty inspired, or at least I was, when I came out here and I found 2 extragalactic objects in the same VERITAS field of view. I was like, wow, we were so lucky just to detect one thing, get 2 in the same field of view. That's awesome. And my friend, who was the director of exhibits at the Arizona State Museum, asked me to create an exhibit, which I put up there. Well, sure enough, a few years later, I picked up a 3rd object in that same field of view. All right, well, that seemed like quite the progress. You know, a few more years later, we now have 6 objects in that field of view, and now we're making constellations. So we really are real astronomers at this point. And the short story is there's now a 7th object up here by the year. So, you know, we were really moving forward. And so it's kind of a lot of fun. So going back to some models and a little bit of hard science, this is what a work from one of my postdocs. This is, again, power, so how bright it is versus energy. So low energy, high energy. So you have radio, or this is optical, X-ray, gamma ray, VERITAS. And what you see here is the best model of the emission driving through it. The data now are so good with VERITAS and all these satellites that not only can you come up with a model that drives through these things, but you can now, this gray area are all of the models that actually work. So you can actually now constrain, like, this is what's possible. And this allows you to then say what range of parameters work. And so you can say, okay, the magnetic field, we know it to within a factor of 2. Okay, how many particles are in there to a factor of 2? And while a factor of 2 is pretty lousy when you're building bridges and towers and things, in astrophysics, that's amazing. Well, VERITAS is a lot of fun. And there's me in the focus taking a picture. You go up on the platforms, which you can do on the VERITAS tours. It's really an inspiring kind of vision to go up there and see. And if you're lucky enough and have a man lift, you can actually go to the 2F point and get your face the size of a mirror dish. But that takes some special friends. This is Dave Fegan. He's one of the founders of the field, so as we set it up for him. And one of the special things that I like to do that's most fun is detect quasars at redshift 1. And why is this? Well, emission coming from a quasar, remember, these are the jets, okay? They shoot off gamma rays, and as they propagate to you, gamma rays get absorbed, okay? They interact with other photons, optical and inert photons. So a gamma ray hits another photon, it creates particles, it creates an electron and a positron, and it just goes away. So as you get further and further away, it gets harder and harder to see. But the thing is that we don't know how much light is there. We don't know how much infrared and optical light is there. So if there's a lot of light, you're going to get a lot of absorption. And so if your spectrum, this is power versus energy, if there's a lot of light, you'll get a lot of attenuation. And if there's less, you'll get less attenuation. So you'll see more at the observer. So detecting something far away, you're A, going to try to, it's hard, but B, you'll be able to measure how much absorption you have. So in 2015, we detected something at a redshift of 1. That means that light traveled halfway across the universe for us to see it. It was emitted almost 8 billion years ago, the stuff that we saw. Okay, well, that's tough, but actually, it isn't unusual that we saw this. This is the emission from a Fermi satellite. It's not absorbed. This is what we saw. And what you can do is then you can throw an EBL model in there and you say, okay, how much EBL was there in order for the line basically to line up with the Fermi emission, the unabsorbed stuff. So you can measure the extragalactic background. And that's what this plot is. This is the range of, this is how much light we said. This is how much EBL there could be, this blue curve pointing down. Okay, other people have tried this. If you just count up all of the galaxies in the universe in optical and infrared, and you say this is how much light they've emitted, that is the minimum. And so basically what this measurement allows you to say is that there's no other light in the universe other than that emitted by galaxies and stars, optical and infrared. And this is very important for dark matter theories, exotic stuff like this. Well, I'm going to show you now something that's so hot off the press, you will be the first in the world to see it. January 24th, 2005, we detected a flare after an alert from the gamma ray satellite of something not at redshift 1, almost, but at redshift 0.997. Light traveled almost 8 billion years for us to see it. And this may provide even deeper constraints, really hitting those red points that we saw. And so we've been hammering it past few nights. Obviously, it's been a little cloudy the past couple of nights in the snow. It's been unfortunate. So this is just one night we put out an astronomer's telegram to tell the world, hey, look at this. It's going to go away. These things don't stay bright forever, and you know, be able to see it again. But yeah, you're the first to see it. All right. So obviously you can use one galaxy or many galaxies to see this. And what we did a few years ago is we said, okay, take all of these distant galaxies that we see. You know, what does the spectrum look like? What could this extragalactic background light be? And this is now our limit. This is the range, if you will, of possible models, or you know, how much light there could be. That's what's allowable. These are the actual measurements from counting up the galaxies out there. And you can see all of those are basically below the actual amount of light. We pretty much nailed it. Like you say, it really does have to be just the galaxies out there. And this really causes trouble for people that want to create crazy theories. A population 3 stars. I won't bore you with all the details, but you get the idea. All right, well, VERITAS is now 20 years old if you count the prototype. What are we doing in our latter days at sunset? Well, we're still trying to detect flares. Here's the brightest ever flare seen. I showed you that one flare of Parks 2155. This is Markarian 421, the second ever known TeV source. Okay, we detected it at 30 Crab. The Crab is the brightest source in the TeV sky. And you can see that this thing is not varying on 1 minute time scales. It's more like 20-minute time scales, but still 30 Crab. Holy cow. So we're still trying to catch events like this, because it really is very hard to do something like this and trying to understand what this is. And maybe not every event is quite so spectacular like this in terms of brightness or rapidity, but all of these flares tell you something. They maybe allow you to do measurements of cosmology like I just discussed, or something else. And here's a something else. So we detected a flare of BL-LAC. This is the prototype object for these blazars. These things where it pointed right at you. And in 2011, right before sunrise, we caught a flare. This is the trailing edge of his flare. You don't normally see it. And one night, bang, and then it went away and gone. And it reached 1 Crab, the brightest source in the sky, and it decayed on a 13-minute time scale. All right, well, that's kind of fun. But our friends were looking at it with the radio telescopes. And what they saw coming out of the jet is that you have the core, this black hole at the core, and then something was born that they call a knot. So a piece of material was released right next to the black hole. Okay, and so whatever was causing this flare seems to be related to the birth of a new feature very near the edge of a black hole. All right, well, that's very interesting. See it once, you might want to see it again. Oh, hey, lo and behold, in 2016, we see another flare right there. You know, it's nicely resolved, real nice structure, you know, rising on a couple-hour time scale, fall off on a half-hour time scale. And once again, here you're monitoring it, and another knot comes out of this jet. Okay, another blob of material coming out. So with these flares, you start to understand what may be causing them. Now, many of you may have heard of the Event Horizon Telescope and may have seen this image. This is the rim of a black hole. This is done in radio. Every year, we run a campaign with them. We observe at the same time. The idea being is, okay, we're seeing these knots. That doesn't tell you a lot, but this is the most high-resolution telescope in the world. And so we look at an object called M87. It's gone off, you know, a bunch of different times. You know, you see it flare, okay, and you can see that it flares on all these things in radio as well. And so we're just waiting for this object to flare one more time. While Event Horizon Telescope is looking, every April we look with Event Horizon Telescope to see if they can get a different Ring of Sauron kind of thing for us. And that will tell us something. So that's another big project we're trying to do moving forward. But the biggest thing we try to do is neutrino astronomy. Okay, back in 2017, a couple hundred TeV neutrino went through the South Pole ice. And down there they have photosensors. And you can see how it just lit up this string of photosensors in the ice, giving off Cherenkov radiation in the ice. And lo and behold, VERITAS and a couple other gamma ray telescopes detected a flare from an AGN. Okay, so neutrinos coming from this AGN at the same time as gamma ray emission, which means that it's a proton accelerator. Okay, and this was called the birth of neutrino astronomy. But one of the things that's really important to do is you will see it once, but you really need to see it a few times before you can really say something. And so we've been searching and searching and searching now for 8 years for a repeat event. We've had one that was about 3 sigma, so 1 in 1,000 chance. But we have this gold standard of 5 sigma in science. We try to be that. We haven't caught it yet. So this is something that we're desperate to try to do again. We also do optical astronomy, where we measure occultations of stars, asteroids passing across. So when an asteroid passes across a star, you can imagine that it gets a little bit dim for a while and then rises back up, but you get these wiggles. Okay, and using the wiggles, you can actually measure the diameter of a star, something called a milliarc second. It's an absurd level of precision. There's no other device on the planet that can even measure close to this. So you're measuring the diameter of a star to 1% accuracy. We do something called stellar intensity interferometry. Okay, a lot of quantum physics there. I'll kind of leave it at that so we don't all get confused. But we're basically measuring the diameters of stars and making catalogs. And as you can see, nature seems to think that's pretty important. So some of the other things we're doing in our days. But the idea is to take an image that looks something like this and making it much, much more crisp. Okay, well, what are we doing after sunset in my closing minutes here? We're trying to build something called the Cherenkov Telescope Array Observatory. And the idea is to enable more than 1,000 sources and population-based astronomy, not just one supernova remnant, but hundreds. Try to really understand things. If you looked at humanity and tried to base all your conclusions based on me, you'd probably get some pretty weird thoughts. Not everybody's blonde, not everybody's 6'2", you get the idea. So what this will do, and you can see it here, is it's going to improve the sensitivity by a factor of 10 and the angular resolution by a factor of 3, which really means 10 times as many pixels in your images and reducing the time to detect sources by a factor of 100. So you heard 30 seconds from a crab, now you're talking less than a second. Amazing stuff. The construction's ongoing. It's going to be partly ready by 2028. And when we have enough money, it'll be finished. Okay. We just got 350 million euros a couple of weeks ago. We were drinking champagne up at Wildflower in the foothills because, that's a pretty big deal for us. But what you see about CTA is it has big telescopes. These are 23 meters across. It has medium telescopes, which are 12 meters across, and it has small telescopes, which are about 4 meters across. It's a big project, 1,500 scientists, 150 institutes, 25 countries. It's very expensive. And here's a group of kind of 200 core people in Lugano, Switzerland, just before the pandemic, but a good, nice place to be. It's going to be located in the Canary Islands of La Palma and in Chile and Paranal. It's going to be about 100 telescopes down here and about 20 telescopes up there. And the construction's moving fast. You can actually see the La Palma site as it was in August. The 4 big telescopes are under construction. And this is going to, surpass VERITAS in a couple of years. Okay, and this is probably when we're going to start thinking about turning VERITAS off because it's a much more powerful instrument and, we want to use our resources wisely. I'd rather spend American money, doing this than kind of keeping the old machine going. So there's a big book if you want to read about the science. It's available online. It puts me to sleep, so I can imagine the same might be said for you. But just gives you an idea of the sensitivity. Here's VERITAS. We're the most sensitive in the world. And that's where the initial configuration of CTA will be. Final configurations will be down here. And this is like basically lower is better, more sensitive. What is CTA going to see? Well, this is the galactic plane survey. They're expecting about 500 sources, lots of dots, big ones, little ones, diffuse emission. Looks pretty impressive. It's also going to have vastly improved resolution. This is what a supernova remnant looks like in X-ray. This is what it kind of looks like now with the current resolution. This is what it'll look like with CTA's resolution. Why is resolution important? Well, you'll be able to understand whether it accelerates leptons, meaning electrons, or protons just based on the shape. Your eye can tell you, right? You see it. You don't need to have these fancy models that are really confusing and all these satellites. And, so if you just look at it, oh, yeah, protons, makes it a lot easier. What are we doing in the US for it? Well, we're building a prototype telescope to contribute to this. It's at the base camp at the Whipple Observatory. If you go on the VERITAS tour, you'll get to see it. And the main thing you'll notice, it has 2 mirrors. It's a dual mirror telescope. The design for this telescope it's highly aspheric. It's based on a 1905 optical design that was so complicated and so difficult, nobody tried it. They said it was impossible. But in 2019, we successfully completed it. And the idea is that when you build a telescope, when you start to get off the axis, you have a lot of aberrations, things that mess up your image. This, through fancy optics, eliminates that, and you have a uniform point spread function across an 8-degree field of view, about 16 moon diameters. Okay. It also allows you to have a very compact camera. And so we'll have 11,000 pixels in this camera, the most pixels ever, instrumented very cheaply. So NSF gave us $5 million to build the prototype. And you can see what images start to look like. This is what it looks like in a standard camera, and you can barely see it here, but it's just very fine grained. That's what the background looks like, and you see structures in there. It really allows you to do things. And basically, this will allow you to see things if you put these telescopes in twice as fast. And it really means a lot. When you're talking about a $1 billion class observatory, getting twice as much time really means a lot. It works. We see the crab. This is the point spread function across the field of view. You see that we have achieved, this is the measurements, what we promised. So we've done it. We succeeded the impossible. We're upgrading the camera at the Whipple Observatory. We had some issues with the electronics, but now we're kitting it out right now. You can see we took it off. We put it back on just this year, and we're commissioning a new camera this year. So this is where the effort is right now. And so we have a lot of good things going. And then I will close, hit the 1 hour mark. Good job. So the first generation of these telescopes started in 1968, and they pioneered a new field of astronomy. It's really the last time we're going to be able to say this for photon astronomy. There's no other band out there. So I'm glad to be a part of it. I started when there were 3, and now there's 300. So, a lot of fun. The first galactic and extragalactic detections were here in southern Arizona at the Whipple Observatory. We're trying to get that recognized with a historical marker out there. It's a fight, but we're trying to get that done. The third generation of instruments really established this field as mainstream, and I think I tried to give you a flavor of the type of things that we do out here. Obviously, I could spend a lot of time talking about it. The VERITAS began its efforts about 20 years ago. Come visit the Science Center to see it. It's really spectacular. You will not see other telescopes like it anywhere, really. I mean, you can't get to Namibia to see those. You can't get to the Canary Islands to see it. So it's really the only place to access it. I have funding to run VERITAS through this summer. Hope to run it till 2028. It's a challenging time. We've put out 140 papers. I've graduated 82 students, out there in the world. Most of them are off in industry trying to do great things. The next generation observatory is CTAO. We're going to have more than 1,000 sources. And the US is planning to put this dual mirror telescope out there to cut time to detect things in half. Much improved angular resolution, and you saw what you can do with that angular resolution, just seeing the physics behind it. And we're also contributing to other types of telescopes, and the reason is that the prototype's going to take some time. Building the best telescope ever takes time to finish, and they're already constructing. So we're chipping into the other telescopes to give us access to the early data, because we don't want the US and our young people to be left behind, while we finish up the best telescope ever. So, and with that, I'll just say thank you for joining and listening today and coming out.